This video is sponsored by Brilliant. Let's just get to the point. Why do we learn differential equations? Because they are the equations that describe how nature works. The universe one day said, boom, here's a bunch of stuff, and we said, cool, how's it all work? And the universe said differential equations. They're tough, often impossible to solve exactly, but you'll eventually get some cool stuff from them. Modeling how a population will grow involves differential equations. How any fluid moves, differential equations. Electromagnetism, which is how phones, radio, Wi-Fi, and GPS all work. Not one, but 4 differential equations known as Maxwell's equations. There's electric circuits, and even if something touches something else, and thus exerts a force, differential equations are used to describe the motion. If there's no physical contact, like with orbiting bodies, there's still a force, so there's still differential equations. Now, as with simple algebraic equations, differential equations can, and often do, have meaning when you read into the story that they're telling. Like, this equation could be saying, my age is Y, and I'm exactly 5 years older than my brother, whose age is X. And we can use this to determine either of our ages given the other. Pretty boring, but we can give it meaning. This equation can have meaning too, or rather it asks a question. And that question is, what curve, or family of curves, have the property where the numerical value of the area under the curve is twice the numerical value of the arc length on that same interval for any given interval a to b? Well, to set this up, we start with this equation, which is the area under the curve itself. And this is the equation for the arc length on that same interval a to b. But we want to know when the left side always equals twice the right side. Now we can differentiate both sides to remove the integral sign, and we're left with a differential equation. From here we can square both sides, and then distribute, and we get that original equation. If you solve for that function y, you'd get this, which is the curve you're seeing here. So that's one example of meaning within a differential equation. But let's see how these really describe some real-world situations, because it's not always obvious what story these equations tell, or how they show up in general. And since I always love bringing up the TV show Numbers when I can, here's a perfect example. So check out this scene from an episode where law enforcement is trying to catch a couple committing crimes as they travel across the United States.
When we plot your movements against those of your targets, the pattern makes itself known.
And when we plot your path against Hoyle and Winters, we got this.
Yeah, this is the Red Desert robbery, the missing point on a curve that I didn't even realize I was looking at. It's a variation on something called a pursuit curve.
Alright, so what's happening here is the FBI has been chasing this couple across the country but hasn't caught them yet. So the mathematicians plotted the paths both the criminals and the FBI took to see if they can make some predictions about where the criminals will strike next. And this is related to pursuit curves. A pursuit curve is simply the curve traced out by one object chasing another, although there are usually conditions listed for something to be technically considered a pursuit curve. But this could apply to a cheetah chasing down a gazelle, or one aircraft chasing another, for example. So let's see how we can determine the curve that the pursuing object will trace out. Now, 2 things to note. First, we're going to assume that the plane being chased has a predetermined path. Whether it's flying straight up, or in a circle, or whatever, assume we already know their path. Then the second assumption, like I mentioned before, is that the chasing object is always moving in the direction of the other, and it turns its nose as needed during pursuit. In reality, this could be like a plane wanting its forward-facing guns always aimed at the target or something. Anyways, what you're seeing here is a snapshot of the chase, and we can represent the current positions of each plane with a vector. I'll say C and M for cat and mouse. The other thing we know is that at this time, or really any time, the chasing plane is pointed at the front one, which means this is their velocity vector, or C prime, at this moment. There's no wind or anything, so the plane is definitely flying in the direction it's pointed. Now, we don't know the speed or the length of that vector currently, but we know the direction at least. That's more important because there's another vector pointing in that same direction, which is easy to find, and that's m minus c. For the visualization, m minus c is the same as m plus negative c, and putting negative c on top of m gives us a vector that points from the back plane to the front one. Then to deal with the lengths, I'm going to normalize the two vectors by dividing by their magnitudes so they both have a length of 1. This is key because the dot product of two vectors, both with length 1 and pointing in the same direction, is 1. This is a fundamental equation. Yes, I could have just set the vectors equal to one another, but I'm doing this because in that episode when the mathematician is explaining pursuit curves, you can see that equation come on the screen, so now you know the meaning behind it. But still, it's not really obvious how to solve it yet. But if we go back to our snapshot, remember that the m vector is actually a known function of time. We're seeing it only at one moment in time, but it is changing as the planes fly around. So I'll say it's a vector function u of t, v of t, which are both known. I'm just keeping things generic. The c vector also changes in time, but it's our unknown, some x of t, y of t that we want to solve for. And the c prime vector would just be x prime of t, y prime of t. So then m minus c would give us this vector here, just the x component subtracted and the y component subtracted. And I'm just not writing the t's so there's room. I'll do the same thing with c prime. Then if we plug all of those into our equation that we want to solve, we get this. Now the one extra thing I did was set the magnitude of c prime to 1. Which just means we assume the chasing plane is flying at a constant speed of 1 just to simplify the equation. Then we just have to do the dot product, which leaves us with this differential equation. You'll notice I actually wrote out the expression for the magnitude of m minus c on the bottom here. The only problem with this is that there are two unknown functions, x and y, which means we need another equation. But that would just be the one saying the chasing plane is flying at a constant speed of 1. Now we have a system of differential equations that can be solved. If, for example, we assume the target plane is flying straight along the y-axis, then this would be the path of the chasing plane shown in red. If the target plane were flying in a circle, then you'd get something very different shown here on Brilliant Sight. Now, you'll notice this method of chasing someone isn't necessarily ideal for catching them, but there seems to be other types or variations of pursuit curves that range from always aiming at the target to predicting where they'll go next. On that numbers episode, the situation was more complex as the mathematicians were accounting for how the moves of the FBI might affect the criminals that were being chased. But still, the basics of pursuit curves can be seen in a first-level differential equations course. And while this might not be a real-world FBI case, pursuit curves can be applied to missile guidance systems, aircraft, submarines, and so on. Alright, now let's look at something more casual. If you go to the gym, you may have seen, or done, a bench press or squat with chains hanging off the sides. This makes it so that as the bar moves up, the chain is more and more suspended and thus contributes more of its weight to the exercise. Meaning, as the person pushes upwards, the weight increases. This actually complicates the equation of motion more than you might think, because for every little dx, or change in height, yes, I'll be using x as the variable, there's a dm, or small change in mass, in regards to the part of the chain that's off the ground. So let's see what this setup would look like. Now, we'll say the barbell has no mass, just to make things easier, so really we're just lifting the chain off the ground, and we'll call that distance off the ground x measured in meters. Then let's give the chain a weight density of 10 newtons per meter. Thus the weight of just the section off the ground is 10x. So if the chain were 2 meters off the ground, then you'd have to use a force of 20 newtons to hold it in place. Then the equation for mass for the part of the chain off the ground is simply the weight divided by gravity. Weight is 10x, and I'll round gravity to 10, as always, so the mass of this part of the chain off the ground is just x. Lastly, we'll say the person is pushing up with a constant force of 50 newtons, meaning the net force is 50 up minus the 10x down from the chain itself. Okay, now before we can move on, we have to realize that F equals ma is a lie. Well, not really, but it only applies to special cases where the mass is constant. The real equation we have to work with is F equals the rate of change of momentum, or mass times velocity. Doing a simple product rule, we get this here. And you'll notice when m is not changing, which we get used to in a first level physics course, then this term is 0, and we're left with F equals m times dv dt, or F equals ma as usual. But with the changing mass, we have this entire equation. From here, I'm just going to replace the variables, like mass is really x, and force is 50 minus 10x. So we get this here. But velocity is just the rate of change of position, and dv dt, which is acceleration, is the second derivative of position. So we're left with this equation here. Moving the 10x over, we're left with a second order nonlinear differential equation. Solving this would not be easy, but not really the point of this video. Instead, I just want to highlight that the motion which results by something as simple as pulling a chain upwards has to be expressed through a not so simple second order differential equation. And while it may be true that analyzing the motion of a barbell isn't too applicable, the idea of analyzing a system with changing mass is. The perfect example is a rocket. As exhaust leaves the bottom, the rocket itself loses mass little by little. So thrust and a changing mass are kind of linked, and this situation also leads to differential equations. But now let's look at the most real-world application I can think of. This here is a curve of the number of currently infected people from the coronavirus as of early June. It's infected people versus time, which means the instantaneous rate of change or slope at any point is di dt. It gradually increased for a while before flattening out, but we want that rate of change to go negative. Anyways, this is an incomplete picture of what's going on because there are other categories of people out there. In the population, there are those that have never been infected or those that are susceptible, those that are currently infected, and then those that are recovered or, unfortunately, deceased. But the most basic model, the SIR model, just calls it recovered and assumes no deaths. I know many YouTubers have talked about this recently, so I'll keep it kind of short. In the case of the coronavirus, everyone started in the susceptible bucket, and let's say the population is 20. So no one is infected, but everyone has the potential to be. And then one day, one person transitioned to infected. This was basically an initial condition. Now, if the population stays constant, no one new is born, then the number of susceptible people can only go down or stay the same, because as soon as you get infected, you leave that group never to return, assuming immunity after you get the disease. So the rate of change of susceptible people is going to be negative something. It can only go down. Since having a lot of infected people or a lot of susceptible people / a high population increases the magnitude of that change, then we say it's S times I, where S and I are the number of susceptible and infected people respectively. If either of these are large and the other is non-zero, you have a large transition to those who are infected. But we also have to include a constant. That constant depends on the virus and us, as it scales how quickly people go from healthy to sick. Social distancing or hand washing, for example, would decrease that constant, and this rate of change wouldn't be as extreme. Then the rate of change of those who are infected starts with that same expression seen on the left, but positive. This is because in this model, it's a one-way street. If someone leaves the susceptible pile, they go to infected. But people will leave the infected pile, proportional to how many infected people there are. This constant, in reality, is death rate combined with recovery rate. If medicine is released that speeds up recovery by 50%, then that constant goes up and people are quicker to leave the infected pile and become recovered. The rate of change of those who have recovered can only be positive or zero, and it's that same constant times I. You'll notice in this model that we kept the population constant, so the sum of the three categories was always the same, meaning the rates of change should add to zero as they do. But here we're left with another system of differential equations that, when solved, will tell you how an infection will spread through a population in this simplified scenario. I'm sure many of you have seen Numberphile's video on this that I'll link below, but there you can see what happens when you play around with the equations and constants and all that. As with most of these examples, we did simplify things to make the math easier, but this is all the foundations of what's going on in the real world. If you go to the website for the International Council for Industrial and Applied Mathematics, there's a page on the mathematics of COVID-19, showing the simulations and models that mathematicians are creating to understand the spread of this virus in different parts of the world, where you'll find equations just like we saw. Equations very similar to these also show up in terms of population growth. One of the first differential equations a lot of us learn is the one that models how a population will grow at a rate proportional to its current value. The more people or animals there are, the faster the growth as expected. But things get more complicated with deaths or when maybe one population kills off another. Here's an example of bacteria which can multiply on their own, and phages that essentially feed off bacteria and thus will die without them. And you'll see that after one cycle here, the phages grow from 1 to 4, but the bacteria stay at 2. And now there are more phages, so some will die while others will continue to multiply. So there's kind of this back and forth that happens, but it leads to differential equations where the rates of change depend on multiples of the populations. And it's not always about just solving the equations, as there are tools such as phase portraits that can help paint a picture about what's going on without having to find an actual solution. Here, if you're given a certain population of phages and bacteria, this would tell you how the system, or really both populations, will change at that moment. And with this we can find equilibrium points or long-term behavior, for example. And while I'm not going to go any further than this, I think we've discussed a lot. If you want to dive more into the topic of differential equations, you can of course do so right here at Brilliant. Currently they have 2 differential equations courses which are some of my favorites because of how much they focus on real-world applications. They have the pursuit curves we discussed, there's 2D and 3D wave equations, there's the equations that model the behavior of beams, and much more. Their first course does start at the basics for anyone just starting out, but by the second course there are things I never saw as an engineer in college, so regardless of where you are in your education, there likely is a lot to learn whether you want to get ahead as a student or just brush up on old topics. So if you want to get started right now and support the channel, you can click the link below or go to brilliant.org/ZachStar. Plus the first 200 people to sign up will get 20% off their annual premium subscription. And with that, I'm going to end that video there. Thanks as always to my supporters on Patreon. Social media links to follow me are down below, and I'll see you guys in the next video.